Time, the ticking heartbeat of the universe. A silent rhythm woven into every atom, every breath, every star. It moves forward, never backward. Relentless, measured, absolute. Or so we once believed. But what if time had a beginning, a first moment, first tick? And if it did, what then came before? This question, simple on the surface, cuts deeper than any telescope can reach. It is echoed through temples and laboratories alike. It's whispered beneath the stars by ancient storytellers and written in equations by modern physicists. Where did everything come from? It's not just matter and energy, but space itself, time itself. Was there a before? There's the very idea of before, a trick of language, a word without meaning at the beginning of everything. We peer into the sky, past galaxies and quasars and fading light, until the view dims and vanishes. Beyond that veil lies a silence we cannot yet penetrate, a boundary not just of space, but of understanding. Here, at the very edge of what we can know, science meets philosophy. Theory touches mystery, and awe becomes our only compass. Tonight we leave the world of clocks and calendars behind and turn our gaze to the edge of time itself. 13.8 billion years ago, everything began. It's not just stars and planets, not even space or matter or light, but everything. It's time itself. It's a concept that resists comprehension, not a place, not a bang, as the name misleadingly suggests, but a moment, a singular, incomparable moment, when reality as we know it bloomed from a seed of infinite potential. What existed before that moment? We'll return to that question soon. But first, we must understand what we can see. What we do know, at the very beginning, the universe was smaller than an atom. Singularity, as some call it, though even that word borrowed from the language of black holes, is a placeholder for mystery. In that unimaginably dense speck, all the energy, all the forces, and all the laws of physics that govern our world were compressed into a single point. Then, in a fraction of a second, far shorter than a blink, shorter than a heartbeat, began to expand. Not like an explosion from a central point into empty space, but something far more radical. Space itself was stretching. Time itself was beginning. What was once nowhere, it became somewhere. This is the event we call the Big Bang. Not a burst of fire and fury, but the rapid unfurling of space-time. In that earliest epoch, the universe was unimaginably hot. Temperatures soared into the trillions of degrees. Particles, quarks, leptons, gluons flickered in and out of existence, dancing in a chaos of unimaginable energy. And yet, even in that chaos, patterns were forming. Within the first trillionth of a second, the universe entered a phase of cosmic inflation, exponential expansion so fast and so vast that what was once subatomic in size became, in a breathless instant, the scale of galaxies. Inflation didn't just stretch space, it flattened it, smoothed out its wrinkles, and it seeded the structure of everything that would follow. Quantum fluctuations, those jittery, spontaneous variations born of uncertainty, were magnified to cosmic scales. And over time, they became the blueprints for everything: galaxies, clusters, filaments, voids. From quantum flickers came the architecture of the universe. As inflation slowed and the universe settled into more gentle expansion, its temperature dropped. The raw energy of the early fireball began to organize. Quarks joined to form protons and neutrons. Some neutrons decayed, others were caught in the crucible of fusion. In the first few minutes of existence, the first atomic nuclei were born: hydrogen, helium, and a trace of lithium. These would become the raw ingredients of every star, every planet, every living thing. This brief, vital window known as Big Bang nucleosynthesis lasted only minutes, and yet its fingerprints remain etched across the cosmos. Even today, the precise ratios of hydrogen to helium to lithium we observe match exactly what those early moments predicted. It is one of the great triumphs of human thought. Our models match the sky. But despite this clarity, the universe in those early minutes was not yet visible. Light could not travel freely. The cosmos was still opaque. A dense, radiant fog of charged particles and trapped photons. A fog so thick, so chaotic, that light itself couldn't move more than a fraction of an inch without colliding and scattering. This was the early universe, bright, hot, and hidden, and so it remained for 380,000 years. Then something changed. As the expansion continued, the universe cooled further. Finally, the temperature dropped low enough for electrons to bind with nuclei. Atoms formed mostly hydrogen, some helium, neutral, transparent. The fog lifted. And for the first time in the history of the cosmos, light was free. Those first free photons, unleashed in every direction, still exist today. They continue to travel, crossing billions of light years, bathing the universe in a soft, invisible glow. We call this ancient light the cosmic microwave background, or CMB. It is the oldest light we can observe. The CMB is not a spotlight, not a brilliant flash. It is a whisper, diffuse afterglow, a faint echo of a time long past. Invisible to our eyes, but visible to sensitive instruments, it paints the sky in microwaves. And though it appears almost perfectly uniform, there are tiny variations in its temperature, 1 part in 100,000, and these tiny ripples are everything. They are the seeds of all future structure. Tiny differences in density that would, over billions of years, become galaxies. They are the fossils of the earliest clumps of matter, etched into the sky like a baby picture of the cosmos. We see them today as color-shifted maps from satellites like COBE, WMAP, and Planck. To the untrained eye, they may look like static, but they are not random noise. They are the blueprint of all structure, the earliest trace of cosmic order. This light, this ancient whisper from the past, is the farthest back we can currently see. It marks the edge of the observable universe. Beyond that lies darkness. It's not because there was nothing, but because there was no transparency. Before the CMB light existed, but it was trapped, scattered, caught in an ocean of charged particles, not yet free, and yet something did exist before. Physics demands it. Logic requires it. But here the trail grows cold. We now approach a realm where even our most trusted tools, our mathematics, our models, our machines begin to falter. To glimpse what came before that light, we must turn inward to theory, what we call the Planck Epoch. This is the first moment in time that our physics can even begin to describe. The earliest chapter in the book of reality we are still trying to read. It occurred just 10 seconds after the Big Bang. A fraction so small, it defies imagination. 1 second divided 100 billion trillion times. At that instant, the universe was unimaginably hot, unimaginably dense. A place where the familiar laws of nature no longer applied. In this era, gravity, the weakest of the 4 fundamental forces, may have been just as strong as the others. Space may have curved violently. Time may have fluctuated. Particles may have blurred into fields. This is where general relativity and quantum mechanics collide. Relativity describes the large galaxies, stars, the motion of space itself. Quantum mechanics describes the small particles, fields, the flickering uncertainty of matter. But here at the beginning of everything, they must speak the same language. So far, they do not. We do not yet possess a working theory of quantum gravity, a framework that unites these 2 pillars of modern physics. We have candidates: string theory by loop quantum gravity, ideas, clues, mathematics that hint at the truth, but no final answer, not yet. In this unknowable fraction of time, the universe may not have even had the dimensions we now observe. It may have been 2-dimensional, or 10, or none. The fabric of space may have emerged from something deeper, something we haven't yet named. And so we call it the Planck wall, the veil that marks the edge of what we can currently understand. Beyond it lies a universe shrouded in darkness. Not the darkness of night or the cold void between stars, but the darkness of unreachability. And yet we are drawn to it, because it is here that the deepest questions dwell. Where did it all come from? Why does anything exist at all? What laws govern the first breath of time? Did time itself have a beginning? And if it did, what lies beyond it? In that silence we find not despair, but wonder. For every model we test, every theory we explore, brings us closer to lifting the veil, closer to the moment the universe whispered its first word. We cannot yet hear that word, but we are listening patiently, boldly, because the light of reason has never stopped reaching. The closer we get to the beginning, the less we understand. Time, for all its constancy, is not infinite in both directions. There is a past, yes, but not an eternal one. The Big Bang was not simply a moment of immense heat and rapid expansion. It was the boundary between something and everything. And the deeper we try to probe into that first moment, the more the ground beneath our understanding begins to give way. With every step we take back through cosmic history, through the first stars, the earliest galaxies, the glow of the cosmic microwave background, we enter epochs we can model, explain, even map. But as we approach the true beginning, we encounter a wall, not a physical barrier, not the edge of space, but a wall of comprehension, a veil drawn across the very birth of reality. We call this veil the wall of unknowing, and what lies beyond it, if anything, remains one of the greatest mysteries in all of science. This wall sits at a moment known as the Planck time, named after Max Planck, one of the pioneers of quantum theory. It marks the smallest meaningful unit of time we can describe, 10 to the power minus 43 seconds. After the Big Bang, that's 110-million-trillion-trillion-trillion ths of a second. A moment so short that our language struggles to express it. A moment where time itself may have been only just coming into being. At that point, the universe was not just hot, it was infinitely hot. It's not just dense, it was beyond density, compressed into a state so extreme that all known laws of physics break down. This is the singularity in its purest, most inscrutable form, and we have no clear map to describe what it was or how it behaved. To approach this moment is to walk a tightrope between two mighty towers of science: general relativity and quantum mechanics. General relativity, crafted by Einstein, is our most successful description of gravity and the large-scale structure of the cosmos. It describes how space bends, how time dilates, how mass and energy shape the curvature of the universe. It explains black holes, gravitational waves, and the expansion of space itself. Quantum mechanics, on the other hand, rules the microscopic world, the domain of atoms, particles, and the uncertainties that ripple through them. It is a world of probabilities and possibilities, where particles exist in clouds of potential until observed, and where energy and matter flicker into existence and vanish again in the vacuum of space. Both theories are stunningly accurate. Both have been tested and confirmed to astonishing degrees, and both are necessary to understand the full story of the universe. But the moment we try to apply them together to the same place, at the same time, they begin to contradict each other. They describe reality in different languages. One speaks the poetry of curvature and smooth geometry. The other whispers in equations of randomness and uncertainty. At the Planck scale, where the universe was unimaginably small and energetic, both theories should apply, but they do not agree. General relativity breaks down under quantum stress. Quantum mechanics falters under the sheer gravitational intensity. This is the heart of the problem. In the earliest instant of the universe, all for fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force may have been unified. A single, harmonious force. No longer distinct, but one. But we have no clear mathematical framework that can describe this unity. The theories we rely on begin to contradict each other the closer we approach that first moment. And so, at 10 seconds, we hit the wall. Beyond that point, time itself may lose its meaning. Space may dissolve into a kind of quantum foma, turbulent sea, where geometry itself is in flux. Energy and matter may exist only as probabilities. And the smooth, continuous space-time we take for granted may be an illusion. A macro-level approximation of something far more granular, far more alien. Some theorists suggest that, at the Planck scale, space is not smooth, but quantus made of tiny, indivisible units, like pixels on a screen. This idea, at the core of loop quantum gravity, imagines that space and time emerge from fundamental building blocks. Loops of quantized geometry woven together into the fabric of reality. Others turn to string theory, which reimagines particles not as points, but as tiny vibrating strings, edge vibration corresponding to a different particle. These strings operate not in the familiar 3 dimensions of space and 1 of time, but in 10 or 11 dimensions, most of which are curled up, hidden from view. String theory promises a way to merge gravity with quantum mechanics, but its predictions are difficult to test. Beautiful mathematics, still awaiting a mirror in nature. Between these two approaches, loop quantum gravity and string theory, is a shared desire to find a theory of quantum gravity, a unifying framework that can bring the big and the small together. That can describe what happened not just after the Big Bang, but at the Big Bang and, perhaps even before it. Without such a theory, our view remains obstructed. The Planck Epoch stands as a threshold. On one side, physics as we know it. On the other, mystery. This isn't just a technical limitation. It is a fundamental boundary in our knowledge. We cannot build a telescope that looks back beyond the cosmic microwave background. There is no light from earlier times. The universe was opaque. And even if we could detect something from before, we do not yet have the equations to make sense of it. This is why we say the Big Bang was not the beginning of a thing, but the beginning of everything, because it marks the horizon of what we can currently describe. Not necessarily the beginning of reality, but the beginning of meaningful physics. Yet that does not mean we stop. This wall is not a defeat, it is a challenge, a frontier. And across that frontier lies a realm where ideas flourish, where mathematics stretches the imagination, where physicists speak of pre-Big Bang cosmologies, of cyclic universes, quantum foam, and emergent time. Some theories suggest the universe may have bounced contracting before expanding again. Others propose a quantum fluctuation in a timeless void gave birth to space itself. Still more speak of parallel universes, each born from different pockets of an inflating multiverse. We'll explore these daring ideas soon, but for now we linger at the wall. Because this is where science becomes something more, not just an accumulation of knowledge, but a reflection of human longing. A desire not only to understand, but to transcend. There is something profound about the fact that we can even ask these questions. That a species born on a rocky planet, circling a middle-aged star in a quiet corner of a spiral galaxy, can conceive of a time before time. Here, at the edge of knowledge, we are reminded of our place and of our power. We are the universe, looking back on itself, asking not just where we are or what we are made of, but where we came from, why we are here, whether the beginning was really the beginning at all. We must be careful here, not to confuse the unknown with the unknowable. The fact that we cannot yet see past the Planck wall does not mean it cannot be done. Science is not static. It moves, it evolves, it expands like the cosmos itself. What seems impossible today may become the foundation of tomorrow's insight. There was a time when we could not see the structure of atoms, a time when galaxies were thought to be clouds within our own Milky Way, a time before we knew that space could curve or that light could bend. Each of those mysteries had its own wall, and each, in time, was pierced. The wall of unknowing, then, is not the end of the road. It is a new beginning, a place where questions flourish, where curiosity burns, where wonder reigns. The journey through it will not be quick. It may take decades or centuries. But one day, we will find a theory that lets us see beyond, not just with our minds, but with our equations, with tools that can describe, even predict what lies at the very birth of the universe. And when that day comes, the questions will not cease. They will only grow deeper, because beyond the Planck time lies not just the origin of our universe, but perhaps the origin of every universe. A reality greater than our own, a multiverse. A loop, a bounce, a silence we do not yet know. But we are listening, and we are learning. One theory at a time. One equation at a time. One dream at a time. The wall of unknowing may stand tall today, but it will not stand forever. And when it falls, when the veil is lifted, we may finally learn what lies beyond the beginning. We've reached the edge of what we can observe. We've met the limits of the tools we trust. Beyond the wall of unknowing, equations collapse, time loses form, and the universe retreats into silence. But the human mind does not. Where our instruments falter, imagination begins. And with imagination comes theory. Not fantasy, but framework scaffolding made of mathematics and reason, desire to complete the unfinished sentence of existence. This is the realm of bold ideas, of equations that reach beyond the veil. These are the theories that dare to ask, What happened before the Big Bang? Our first theory tonight is the Big Bounce, a universe that breathes. One of the most compelling alternatives to a singular beginning is the idea that the Big Bang wasn't the first moment at all. What if it was a transition? The Big Bounce model proposes that the universe undergoes infinite cycles, periods of expansion followed by contraction. Each universe is born, expands, ages, and collapses, only to be reborn again. In this view, the cosmos is not a line, but a pulse, a living rhythm that stretches across eternity. Imagine the universe as a vast lung, inhaling and exhaling on timescales, so long they dwarf the lifespans of galaxies. After eons of growth and cooling, gravity slowly regains control. Galaxies begin to coalesce. Black holes merge. Matter draws inward. The universe collapses into itself, not into nothing, but into potential. A compressed state of energy poised to bounce outward again. That bounce is what we interpret as the Big Bang. This model finds theoretical support in loop quantum gravity, a framework that suggests space-time is not continuous but quantized, made of tiny, indivisible units. As matter compresses beyond a critical threshold, quantum effects resist further collapse. Instead of a singularity, we get a recoil, a rebirth, and perhaps a memory. Some physicists believe that subtle patterns in the cosmic microwave background the faint afterglow of the early universe contain echoes of a cosmos that existed before our own. Ancient fingerprints pressed into the fabric of time. We haven't found them yet, but we're looking. Our second bold theory tonight is the eternal inflation, the universe that never stopped beginning. Another daring idea suggests that the Big Bang wasn't just a local event, but a local event in a much larger ongoing process. According to the theory of eternal inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang is still happening. Not here, not in our universe, but elsewhere. Inflation, in this model, is a cosmic engine that never shuts off. It continues to drive the creation of new universes, each born as a bubble within an ever-expanding quantum foam. Our universe is just one such bubble. There are others, billions, perhaps an infinite number, each with its own version of physics, different fundamental constants, different dimensions, different outcomes. Some may contain stars and galaxies like ours. Others may fizzle before atoms can form. Some may harbor intelligent life. Others may collapse in silence, forgotten before they begin. In this multiverse, the Big Bang isn't a beginning, it's a neighborhood, one of countless sparks in an endless fire. This idea reframes the mystery. Rather than asking why the Big Bang happened, we now ask, why this one? Why these laws? Why a universe tuned just right for life? Some call this the anthropic principle, the idea that we observe this universe because it allows us to exist. It's not that the universe is designed for us, but that we can only exist in the kind of universe that permits observers. To some, it's an unsettling idea. To others, it's a revelation, a cosmic lottery in which we are the prize, where eternal inflation stretches the cosmos into a tapestry of infinite beginnings. Another theory goes further still. It suggests that there was no before. The Big Bang was not a ripple in an ongoing ocean, but the first drop in existence itself, a singular quantum event, emerging from nothing. But what does nothing mean? Not the absence of things. Not emptiness in a room or the silence between notes. In quantum physics, nothing is far stranger. Even in a perfect vacuum free of matter, free of radiation, there is still activity. Tiny fluctuations, temporary particles, borrowed energy that appears, then vanishes, all within the blink of uncertainty. This is the quantum vacuum, a seething sea of possibilities, and in that sea, the universe may have been born. This idea is captured by the quantum tunneling hypothesis. It proposes that the universe didn't require a cause, only a possibility. In the realm of quantum mechanics, particles can leap through barriers, appear in locations they were never supposed to reach. The rules of certainty are replaced by probability. And from this mathematical truth arises a stunning idea that the entire universe could have tunneled into existence. From no space, no time, no energy, just a quantum fluctuation. Imagine a state of perfect balance, no dimensions, no clock, no contents, an eternal stillness, until one moment. Probability tips. A fluctuation breaks the symmetry, and reality begins. From pure potential comes structure. From symmetry comes form. From nothing comes everything. This is not science fiction. It is rooted in the mathematics of quantum cosmology. Some models even suggest that the total energy of the universe may be exactly zero. That the positive energy of matter is perfectly balanced by the negative energy of gravity, a cosmic ledger with zero sum. If this is true, the universe did not need a push. It simply happened because it could. Of course, such an idea is unsettling. We are trained to look for causes. It's believed that every effect must have a cause, every fire a spark. But quantum theory suggests otherwise. That at the deepest level, reality is not deterministic. It is probabilistic, statistical, and existence itself may be the ultimate fluctuation. This doesn't make life meaningless, it makes it miraculous. Because in a universe that needed no reason to exist, life still found a way to ask questions. To build cities, compose music, and wonder what came before the first light. Some physicists push this even further. They imagine a pre-geometry, a kind of materiality in which time and space are not even emergent yet, where the laws of physics are not laws at all, but possibilities waiting for realization. And then, at a quantum threshold, those possibilities collapse. One universe takes shape. Ours. Too many? This theory is difficult. Not because the math is weak, but because it challenges the deepest assumptions we hold. It asks us to consider that nothing is not nothing, that cause and effect may not apply at the deepest levels, that reality just is. And in this model, the Big Bang was not a divine act, or a reset, or a transition. It was a quantum event. And like all quantum events, it may happen again. Elsewhere, always, we return to the mystery. Not to erase it, but to celebrate it. So we are left with two radically different stories. In one, the universe is one bubble among countless others, an infinite cosmos where beginnings are constant, and we are one of many possible outcomes. In the other, there is no before, no foam, no tree, only the trembling of nothingness and the spontaneous birth of all things. Both challenge what it means to begin. Both reshape our understanding of existence, and both may, in time, lead us closer to an answer. But for now, they remind us of this, that the cosmos is more than stars and space. It is a mystery written in math, a story whispered in light, and we are part of that story. Born not just into the universe, but into the question of how it began. Not all theories about the beginning of the universe propose a beginning. Some dare to ask a more radical question. What if the universe never truly began at all? What if what we call the beginning, the Big Bang, was simply the latest verse in an eternal rhythm? A universe not born from nothing, but reset from something. This is the vision proposed by Nobel laureate Sir Roger Penrose, whose work has shaped our understanding of black holes, entropy, and the geometry of space-time. His theory is called Conformal Cyclic Cosmology, or CCC, and it reframes our entire concept of time. Unlike other cyclic models, CCC does not rely on a universe that rebounds, shrinking, collapsing, and exploding outward again. There is no crunch, no dramatic reset. Instead, Penrose suggests something subtler and more elegant. He proposes that the end of one universe far into the future can be smoothly transformed into the beginning of another, not through a physical collapse, but through a change in the scale of the universe's geometry. Here's how it works. As the universe continues expanding, stars burn out, matter decays, and black holes evaporate through Hawking radiation. Eventually, everything that has mass will disappear. What remains is an ultra-sparse sea of radiation, with no meaningful differences between one region and another. When the last particles with mass have decayed, the very notion of time measured through change, motion, and clocks ceases to function in any recognizable way. In this ghostly future, time becomes undefined. And when scale no longer has meaning, something remarkable becomes possible. The geometry of that cold, infinite future becomes conformally equivalent to the hot, dense geometry of a new Big Bang. What does conformal mean in this context? In mathematics, a conformal transformation preserves the angles between lines but not their absolute sizes. It changes the scale, but not the shape. Think of blowing up a balloon with a world map printed on it. As the balloon expands, continents grow farther apart, but the angles between coastlines remain. The shape is conserved even as the size changes. Penrose applies this idea to the entire universe. He argues that once all mass disappears, when everything that exists travels at the speed of light, then the scale of the universe becomes irrelevant. And at that moment, the final state of one universe can be mapped into the beginning of another. The vast, cold cosmos becomes under conformal transformation, indistinguishable from the conditions of a new Big Bang. This new beginning doesn't arise from destruction. It emerges from geometric continuity. Penrose calls each of these universe cycles an eon. An eon begins in a hot, dense Big Bang, expands over trillions of years, cools, decays, cues, loses its structure, and eventually becomes conformally transformed, not into chaos, but into the next beginning. Each eon passes the torch to the next not by fire or collapse, but by a transition in form. No bang, no crunch. Only continuity, and perhaps communication. Because Penrose believes that information might cross from one eon to the next. If CCC is correct, our universe may carry faint traces of the one that came before. Specifically, Penrose suggests that massive black hole collisions from galaxies long gone in the previous eon could leave behind patterns that survive the transition. These remnants, he argues, would appear in our universe's cosmic microwave background as concentric rings of slightly lower temperature. These are called Hawking points, named in honor of Stephen Hawking in his work on black hole evaporation. Penrose claims to have detected evidence of such circles using real CMB data. Independent analyses remain skeptical. Some dismiss the patterns as noise. Others remain intrigued. But the idea is extraordinary, that we may be living in a universe subtly marked by cataclysms from a cosmos long dead, that our sky carries memories. Most cosmological models treat time as linear, a one-way arrow from low entropy to high entropy, from order to disorder. But CCC reimagines time not as an arrow, but as a circle not closed, but open-ended, ever-renewing. In this framework, entropy, the measure of disorder, doesn't increase forever. Instead, as matter fades away, entropy becomes meaningless. Without matter to change or decay, there's no system to disorder. Time, in this final future, becomes as featureless as it was at the beginning. And so it begins again. This is not a violation of thermodynamics. It's a redrawing of its boundaries. CCC doesn't reverse time. It erases its significance, then reinstates it with each new eon. Time, like geometry, becomes an emergent feature, not eternal, but recurrent. If CCC is correct, our universe may carry faint traces of the one that came before. Specifically, Penrose suggests that massive black hole collisions from galaxies long gone in the previous eon could leave behind patterns that survive the transition. These remnants, he argues, would appear in our universe's cosmic microwave background as concentric rings of slightly lower temperature. These are called Hawking points, named in honor of Stephen Hawking and his work on black hole evaporation. Penrose claims to have detected evidence of such circles using real CMB data. Independent analyses remain skeptical and dismiss the patterns as noise. Others remain intrigued. But the idea is extraordinary, that we may be living in a universe subtly marked by cataclysms from a cosmos long dead. Our sky carries memories. Most cosmological models treat time as linear, a one-way arrow from low entropy to high entropy, from order to disorder. CCC reimagines time not as an arrow, but as a circle not closed, but open-ended, ever-renewing. In this framework, entropy, the measure of disorder, doesn't increase forever. Instead, as matter fades away, entropy becomes meaningless. Without matter to change or decay, there's no system to disorder. Time, in this final future, becomes as featureless as it was at the beginning, and so it begins again. This is not a violation of thermodynamics. It's a redrawing of its boundaries. CC doesn't reverse time. It erases its significance, then reinstates it with each new eon. Time, like geometry, becomes an emergent feature, not eternal but recurrent. If CCC is correct, the consequences are vast. It suggests that our universe is not the first nor the last. It reframes the Big Bang, not as a singular miracle, but as part of a deeper, infinite structure of connected epochs. It also offers a new perspective on cosmic fine-tuning. Instead of asking why the universe is just right for life, why the constants seem tuned to allow atoms, stars, and chemistry, CCC hints that these conditions are not rare or fragile. They may be the default state of every eon. If entropy resets, if geometry loops, then universes like ours may occur naturally, not occasionally. And if each eon can carry information from the last, then perhaps the fundamental constants of nature are not arbitrary. Perhaps they are inherited. The universe may learn from itself. Critics point out that CCC, while elegant, makes few falsifiable predictions. The CMB circles remain debated. The mechanism of conformal transition is not yet embedded in a complete quantum gravity theory. Some argue CCC is a beautiful narrative, but not a testable one. Penrose, however, defends it with characteristic clarity. For him, CCC is not speculative poetry. It is mathematics. Rooted in well-understood transformations and known properties of light, geometry, and decay, he does not claim it is complete, only that it is consistent. A model that fits what we know, dares to answer what we don't. CCC doesn't just change how we see cosmology. It challenges how we see ourselves. If universes come and go, if patterns echo from one eon to the next, then perhaps we are part of something much older than we think. Not reincarnated in spirit, but recapitulated in form. The laws that shaped your neurons, the constants that enable thought and memory, these may have existed before and may exist again. It's not as copies, but as consequences. The universe doesn't remember us personally, but it may remember the conditions that allowed remembering to exist at all. Conformal cyclic cosmology is not the most popular theory of the early universe, but it may be one of the most profound. It doesn't attempt to remove mystery, it reorients it. It tells us that beginnings are not absolute, that time can lose meaning and gain it again, that endings are not terminations, but transitions. And it tells us, perhaps for the first time in modern cosmology, that the universe might have a memory, not of individuals, not of civilizations, but of form, of structure, of possibility. We live in one eon, one brief chapter, but perhaps in some strange and subtle way, our chapter touches the next. Now we shall dive into the last theory of this part, one of my favorite. And the deeper we explore, the more reality begins to shimmer. It's not vanish, but transform. It begins with a simple question. What is space? We move through it. We measure it. We imagine it as a stage upon which matter performs. But what if? Space is not the stage. What if it's the illusion? In our search for the universe's origin, we followed the trail of particles, of forces, of temperature, and geometry. But there is another path, one that leads not to matter or motion, but to information. This path leads us to one of the strangest and most transformative ideas in theoretical physics. It's called the holographic principle. The holographic idea didn't begin with the Big Bang. It began at the edge of a black hole. For decades, physicists wrestled with a paradox. When something falls into a black hole, what happens to the information it carries? The laws of quantum mechanics insist that information cannot be destroyed, but general relativity suggests that anything entering a black hole is lost forever. This conflict is known as the black hole information paradox. But in the 1970s, Stephen Hawking and Jacob Bekenstein uncovered something astonishing. They discovered that the entropy measure of information inside a black hole isn't proportional to its volume, as one might expect, but to the surface area of its event horizon. This meant that the information describing what's inside a black hole could be fully encoded on its surface. It's like looking at a three-dimensional object. It's only to learn that everything about it is described by a two-dimensional skin. This was the first clue, that perhaps reality is not what it seems. perhaps the volume of space we inhabit is not the fundamental level of reality. Physicists began to wonder, if this applies to black holes, could it apply to everything? Could the entire universe be described not by what's inside it, but by what's at its boundaries? The holographic principle, fully developed by physicists like Gerard T. Hooft and Leonard Susskind, proposed that all the information within a volume of space can be encoded on its surface. Just like a hologram where a two-dimensional film can encode a full three-dimensional image, the universe may be a projection from a more fundamental, lower-dimensional reality. Our three-dimensional world with depth and form may emerge from a fabric that itself has no volume at all. This wild idea gained serious traction in 1997, when physicist Juan Maldacena proposed a mathematical framework now known as the ADS-CFT correspondence. In it, a type of space called de Sitter space, a curved universe with gravity, was shown to be equivalent to a conformal field theory on its lower dimensional boundary. Without gravity, two radically different descriptions, one with volume, one without, and yet identical in terms of the information they carry. This was not metaphor. It was a precise, testable duality. And though our universe is not de Sitter in shape, the principle behind it suggested something far more profound, that gravity itself and the fabric of space and time may emerge from quantum information on a lower dimensional surface. If the holographic principle is true, then the Big Bang may not have been an explosion within space and time. It may have been the activation of a code, not a code in the way computers understand it, but a set of informational rules probabilistic, mathematical, that began to unfold, projecting the universe from a distant, inaccessible boundary. In this model, geometry itself emerges from entanglement, the quantum connection between particles that transcends distance. Space is not a static background, but a network of relationships, a tapestry woven from correlations. Time, likewise, may not be a dimension, but an emergent ordering of events. The Big Bang, then, was not the start of expansion, it was the start of interpretation. The moment when the universe began to decode its own informational structure into what we perceive as stars, galaxies, matter, and meaning. This idea sounds like science fiction, so much so that it's become a common theme in films and books. But this isn't the Matrix. This isn't a simulation in a computer. This is deeper. We are not less real, because we may be emergent. Just as the image in a mirror is not fake, it is just a projection from a different source. If the universe is a hologram, we are still part of it. We are still made of atoms and time and thought. But we may not be what we appear to be. The holographic principle invites us to think of the cosmos not as stuff moving through space, but as information flowing through structure. In this view, the fabric of the universe is not space or time, but data. It doesn't travel. It interrelates. It's like a book, where meaning arises not from ink or pages, but from pattern. This idea has found echoes in other areas of theoretical physics. In loop quantum gravity, in quantum error correction, in theories where entanglement creates spacetime itself, across these ideas one theme recurs: that information is the true substrate of reality. And the Big Bang may be the moment that structure emerged from entropy. That order arose from potential, that the source code of the cosmos began to run. Despite its elegance, the holographic principle remains incomplete. We do not yet have a holographic model for a universe like ours, flat, accelerating, and filled with dark energy. And we cannot yet point to a screen at the edge of the universe where this information resides. That screen may exist only mathematically, as a boundary we can never reach, but whose structure silently shapes the world we observe. Some physicists believe the cosmic horizon, the furthest edge of our observable universe, may act like such a boundary. Everything within it may be a projection of information encoded on that sphere. And as the horizon expands with time, so too does the space we can perceive. The universe is growing. It's not by expanding substance, but by revealing more of the holographic code. This reframes the ultimate question. If the universe began with a projection, here we approach a realm of abstraction beyond even conventional physics. Some theorists suggest that the universe emerges from a state of pre-geometry, a timeless realm where information exists without form. Others propose that the code itself may be the lowest layer. There is no before the code because the code defines what before means. The Big Bang in this model becomes not a beginning in time, but a beginning of time. The moment time was defined as a useful descriptor of change and the laws of physics. They may be self-organizing rules not imposed, but arising naturally from informational symmetry. One of the most provocative consequences of the holographic idea is its relevance to mind. Reality is fundamentally informational. Then consciousness, our own subjective experience, may also be emergent from deeper patterns. Some researchers have speculated that entanglement may be tied to awareness, that minds are not just housed in matter, but arise from the relational structure of information itself. It's speculative, but it suggests a universe where meaning is not an accident, but a consequence of structure. If true, then consciousness may be as fundamental as gravity, not an epiphenomenon, but an echo of the way the universe holds itself together. Each of these theories is incomplete. None can yet claim victory. They compete, they evolve, they challenge. But they all share one trait: the courage to cross the wall of unknowing. They ask not only what happened, but what could have happened. And in doing so, they stretch the limits of what it means to understand. What lies before the beginning? A bounce, a multiverse, a quantum tremble, the ashes of a previous age. A code on a distant horizon we do not yet know. But we are listening, and this is the beauty of science. Not in its certainty, but in its willingness to embrace mystery, to admit what it does not know, and yet keep reaching. We live in an age where questions once asked only in temples or poems are now whispered in labs and written in the symbols of pure thought. Where myth has not vanished, it is transformed. In this cosmic story, we are not just observers, we are participants. We are interpreters. We are fragments of the code trying to decode itself. The theories that dare are not fantasies. They are maps. They are signals from the edge. And one day, perhaps not today, perhaps not in our lifetime, one of them may carry us across the veil and show us not only what the universe is, but where it came from. We often think of science as a matter of proof, of knowing, of solving. But the greatest questions science confronts are not defined by the answers, but by what the asking does to us. What came before the Big Bang is not just a question about time. It's a test of our willingness to face mystery not with fear, but with wonder. In this moment, this age of algorithms and acceleration, there is something sacred about the slow unfolding of a question whose answer may never fully arrive. There is power in admitting that we don't know. Not weakness, not defeat, but a kind of intellectual honesty that enlarges us. When we face the horizon of knowledge, when our best equations fray at the edges of space-time, we are reminded that science is not about certainties carved in stone. It is about navigating the unknown with tools we know are imperfect. Theories that dare to describe what came before the Big Bang are exercises in humility dressed as mathematics. They remind us we are not finished. The closer we approach the beginning of the universe, the more language begins to collapse under its own weight. Words like before, origin, cause. These were forged in the context of Earth, of days and nights, of falling apples and growing trees. But what does before mean when time itself is emergent? What does it mean to have a boundary when space itself is not fundamental? We use metaphors, bounces, projections, but these are scaffolds. Temporary, we are reaching into the dark with human hands, trying to describe something that may not fit the shape of our thoughts. And yet, we try, because language is not just for describing, it's for becoming. When we describe the universe, we describe ourselves. There is no progress in physics without imagination. There's no equations without dreams. No telescopes without wonder. Einstein imagined riding on a beam of light. Hawking imagined the edge of a black hole from a hospital bed. Penrose saw cycles of universes in the folds of geometry. The idea that we can reason about realities beyond observation, that we can explore before the universe began, is not hubris. It is hope, not the hope of certainty, but the hope that we can grow, that we can stretch beyond our instincts, our fears, our comforts, and dare to ask questions that the cosmos is under no obligation to answer. Science has shown us repeatedly that the universe is not built with human intention in mind. It is not arranged for our benefit. It is vast, violent, silent, and yet we care. We name it stars. We chart its beginnings. We simulate its futures. Why? Because we are meaning-making creatures, woven from the same atoms as stars. But with the strange capacity to wonder what those atoms are doing here, the universe may not care, but that doesn't make it meaningless. It makes it available to interpretation, to appreciation, to awe, and awe is one of the most honest responses we can offer. In asking what came before time, we also confront our own time, our mortality. We are finite beings. We live on average less than a century. Our species so far has lasted about 300,000 years. And yet we study events that happened billions of years ago and try to imagine what came before that. Why? Because the scale of the universe does not diminish us. It contextualizes us. It tells us that we are fleeting, yes, but not irrelevant. We are the cosmos briefly aware of itself. And awareness, even if temporary, gives meaning to the silence. You will not live to see all these mysteries solved, but you are here, alive now, at the frontier of the greatest question ever asked. That is a gift. So what do we do, as a species, once we realize we are standing at the edge of time? Do we turn away, overwhelmed by its scale? Or do we step forward, knowing the path is long and the answers incomplete, but the journey itself illuminating? To explore the origins of the universe is to engage in the longest conversation humanity has ever had. It stretches across generations, from the first myths told under stars to the latest data downloaded from space telescopes, and it belongs to all of us. This is not the domain of specialists alone. It is not limited to physicists or cosmologists or astronauts. If you are human, if you can wonder, you are part of this quest. The tools we build to ask cosmic questions, the telescopes, the colliders, the satellites, are fragile. They require funding. They require trust. They require vision. In a world often focused on the urgent, they are a vote for the important. To fund basic research, to teach science to children, to protect truth in the face of misinformation. These are not just political acts. They are cosmic acts. They declare that we as a species value truth more than comfort, curiosity more than convenience. And they ensure that the next generation inherits not only a planet, but a sky full of questions. Here's a secret. The universe doesn't owe us closure. It may turn out that some questions have no clean answers, or that our brains evolved to navigate forests and fires may never fully grasp the structure of the multiverse or the information paradox. But the act of trying matters. Because in trying, we refine our thinking. We create tools. We teach others. We reach across disciplines and cultures. We build communities centered on inquiry. This way, the search for cosmic origins becomes a metaphor for something deeper, a way of being. To care about the universe is to take a stance. It is to say, this world matters. Knowledge matters. Honesty matters. It is to fight against the gravity of despair. To resist the reduction of life to survival and transaction. To ask what came before the Big Bang is to declare that we are not only here to consume or conquer, but to understand. And understanding, once sought, rarely stays confined. It spills over into empathy, into ethics, into stewardship. It reminds us, if we are alone in the universe, we are precious. If we are not, we are connected. Either way, we have a responsibility. In the end, what will we leave behind? Our monuments will crumble. Our broadcasts will fade. Our names will be forgotten. But the questions may outlive us. They may seed new civilizations, inspire minds yet unborn, fuel discoveries we cannot yet imagine, to be remembered not for what we answered, but for what we were brave enough to ask. That, too, is a kind of immortality. The edge of time is not a place we will ever fully reach. It is a direction, a horizon we walk toward, not because we expect to arrive, but because every step expands what we can see. Perhaps the question is the origin. Perhaps what came before time was curiosity itself. And perhaps that is enough. We began this journey by looking backward, toward the first light, the earliest moments, the mysteries before time began. We followed shadows across galaxies, whispers from collapsed stars, mathematical echoes from universes that may have come before. We asked not just what happened, but what could have happened, and what it means to even ask. What came before the Big Bang? Perhaps a bounce, a quantum fluctuation, a fading eon, a holographic code on the edge of nothing, or perhaps just the quiet breath of possibility waiting to become real. And yet somewhere between particles and poetry, between equations and awe, we find something else. Ourselves, curious, mortal, awake. In the silence before the beginning, we did not find answers. We found the will to search. And sometimes, that is all we need. Because the universe is not just what we observe, it is what we dare to imagine. So we continue, listening, wondering, reaching toward the edge of time and whatever lies beyond. This has been Cosmic Canvas, where the universe is not only studied, but painted in meaning. Until next time, keep asking, keep looking up, and never stop wondering.